Hi and welcome to lecture 2. Myself Rahul, Assistant Professor, St. Thomas College of Engineering and Technology. So in this lecture video, we'll be dealing with the design of a connecting road. A step-by-step process of analysis of a connecting road will be carried out in this lecture video. So as you all know, a connecting road has mainly 4 different parts. Starting with the shank, which is the length part of a connecting road, it is actually an I section. Now, it is followed by a big end and small end. You can see for yourself in the figure. It is a big end and followed by a small end. Now, the big end is connected using a bolted joint, that is by using a bolt and nut. Now, the design of this connecting rod mainly comprises of 4 different steps. Okay, so it starts with the design of the cross section, which is actually an I section, or it is also known as shank. But care must be taken that while designing this I section, the I section from the figure itself, it is very clear that your I section is not a constant I section. That is the I from the top to bottom, the dimension is not same. Yeah, even though the base dimension is same, the length wise it is different, or the height wise it is different. So we'll be designing the center part, and the other two part has to be found out. Followed by this, we'll be designing the big end and the small end bearing. Once it is finished, we'll go to the design of the big end caps and the bolt, wherein we'll be finding the diameter or the nominal diameter of the bolt and the thickness of the big end cap. So let us go in detail with the start of a journey with the design of shank or I section. So as we have already seen from the previous lecture, we have an I section. Right, the I section is having a standard dimension, T being the thickness, and all other dimensions are designed with respect to the basic thickness T. Okay, the width B being 40 and the height being 5T. Right, so once the T thickness is found, the other dimensions can be found out very easily. Okay, so the one of the main objective here in this section is to determine the thickness of the I section. Now, to determine this thickness, all we need to know is the basic function of a connecting rod, or how does the connecting rod transfer the load. So it actually connects the piston with the crank. Therefore, the load acting on the piston is actually transferred to the connecting rod, which is then transferred to the crank. So actually 2 types of loads are acting. One is a PS and a P. Let us eliminate this PS. Let us consider this P, which is the major load which is acting on the piston, and that is due to the power stroke, and that is transferred to PC. But from the figure you can see that there is a very small angular deviation, right? And since this phi angle is very small, and since this is very small, you can approximately take a PC to be equal to P. That is, the load acting on the connecting rod is nothing but the load acting on the piston. Okay, so it is very easy to find the load acting on the piston rod. Okay, so let us begin this one by finding the force acting on the connecting rod, PC. Okay, so this PC can be found out by the relation PC is equal to pi by 4 d square into P max, which is nothing but the cross-sectional area into the pressure. Okay, where D, as you can see from the figure, is nothing but the diameter, is nothing but the bore diameter, and P max is the pressure acting on the piston. So this equation effectively is pressure into the cross-sectional area, which will give you the force. So once this force is found out, the next step is to find the critical buckling load acting on the piston. So to find this critical buckling load, all we have to do is to multiply this load acting on the connecting rod with a factor of safety. As you can see from here, the critical PC is multiplied with a factor of safety, and normally this factor of safety is taken within the range of 5 to 6. You can take either 5 or 6. So we have found the buckling load for this condition, right? But there is actually a standard equation for determining this buckling load, and that equation is called the Rankine's formula. You might have already learned in mechanics of solids that when a column is subjected to buckling, we'll be using the Rankine's formula. So from Rankine's formula, your PCR can be found using this relationship. right? Where your A is nothing but the area of this I section, this cross section I section, and that is given by 11 t square. And the small a is nothing but 1 by 7500, which is the standard value. You can take it as it is. And radius of gyration kxx is nothing but 1.78 t, and sigma c value you can take it as the 330 newton per mm square if it is not given. Now, and all these values you will be getting from the PSG data book, page number 7.123. Now, once this is found, you may directly equate step 2 with the step 3, since both are PCR, and once you substitute all these values in this equation, you will get all the value in terms of t. So directly you may equate and find the thickness t. So once this t is found, the complete dimension of this I section can be easily found out, because all other dimensions are related to this one, right? But always remember, this is actually the center portion, the dimension of the center portion. The remaining two, the portion at the top portion and the bottom portion is pending. So to find this dimension of the base and the top portion, let us name these two portions. Let the base portion be h2 and the top portion be, base be h1 and the top portion be h2. And at the center portion, as we have seen, the height is nothing but 5t. At the center portion it is 5t. So with respect to this h, we can define the other two dimensions, which is h1 and h2. So the height as at the small and h1 is nothing but 0.75. You can take it in between 0.75 to 0.9, and h2 you can take it approximately as per the split. So with this, your basic design for the connecting rod is coming to an end. Basic design of the crankshaft is coming to an end. Now let us move on to the design of the big end and the small end bearing. So here all you have to do is to find the dimension of the big end and the small end bearing. Okay, so these bearings are actually something that is kept inside this big end and small end, right? So it is effectively a simple hollow cylindrical section. Okay, so let us enlarge this view. So your small end will be looking something like this, as you can see from the figure. Okay, so this is the bearing bush. So all you have to do, or all you have to find out, is actually the diameter of this one, as well as the length of this bearing, diameter of the bearing and length of this bearing. So once you found these two, your design procedure is over. Okay, so effectively the objective here is to determine the dimensions of small end, which is LP, and the dimension of and the diameter, right? Now this subscript P is used because this portion is attached to the piston pin. So to denote piston, this subscript P is used, right? Now the concept behind this is actually the load acting on the piston is actually transferred to the connecting rod. The same load is transferred to the big end and small end bearing as well, right? For the load acting on the small end bearing can be found out using the equation PC is equal to dp into LP into PBP, right? But this dp into LP will give you the area, the projected area, which is the affected area. Actually, this will give you the projected area, and that is multiplied with the allowable bearing pressure. Okay, but the PB is your allowable bearing pressure. And this allowable bearing pressure, you can take it in between 10 to 12.5. This value will not be given. You have to keep it in mind, right? The bearing pressure is 10 to 12.5. Okay, now to find these two, let us equate this value with the standard PC, or the load acting on the connecting rod, which we have already found out, right? The load acting on the connecting rod is nothing but pi by 4 d square into P max. So to find the this one, you also need a relationship, and the relationship is the ratio of length to diameter can be taken anywhere in between 1.5 to 2. So using these three equations, you may equate and you can determine the value of LP and DP. Okay, now the same concept can be applied for determination of the big end bearing as well. It applies, all the same concepts applied applies similarly to this one. Okay, the only thing is that the denotation is will be denoting in it as different way, that is LC and DC, because it is connected to the crankshaft or the crank pin. Okay, now the load acting on the big end bearing is nothing but DC into LC into PBC, where DC into LC is the projected area of the bearing, and that is multiplied with the allowable bearing pressure which is acting on the crank. Okay, now here the allowable bearing pressure is taken somewhere between 5 to 10. So here you may take for both these you may take 10 megapascal, which is applicable for both the cases, and L by D ratio here it ranges between 1.25 to 1.5. So you can take anywhere between this, better take 1.5. Okay, so by equating in the similar way you can find the dimensions, length and diameter. So we have finished that part. Now let us move on to the design of the big end cap and the bolt. Now the objective here is to determine the diameter, the nominal diameter of the bolt and the thickness of the cap. So actually the bolt is the design of a bolt means is to find the diameter. So the maximum force which is acting on the cap and bolt is actually the inertia force which is acting on the piston when it reaches the top dead center during the exhaust torque is the only force which is acting on the cap and the bolt. Okay, so let us move on to the design of this bolt first. Okay, first of all let us analyze the bolt, and after that we will be dealing with the cap. So this is how and the arrangement looks like. And the top end part will look like something like this, where it is having a cap followed by two bolt. So we'll be designing the bolt first. So as we have spoken of the main force that is acting over this one is the inertia force. So this inertia force which is acting on the cap and the bolt is given by a standard equation, and that equation is given as pi max is equal to mr omega square r into 1 plus 1 by n1. And this, let me remind you that this equation is not there in the data book, so you have to learn this equation. So where mr is the mass of the reciprocating butt which will be given, and omega is the angular velocity which can be found out, and r is the crank radius which will be given, and which is followed by n1, which is the ratio of the length of the connecting rod to the crank radius. Now since a pi max force is acting on this base part, this complete the force is actually the bolt actually withstand this force, or it is resisting this force. Okay, therefore the pi max which the force which is resisted by the bolt is given by pi max is equal to 2 times pi by 4 dc square into sigma t. Right, the 2 is coming because there are two bolts, and two bolts are withstanding this one, but sigma t, and the sigma t is actually the permissible tensile stress of the bolt material, which is the material property. Okay, so on equating these two equations for the pi max, we can get the core diameter, which is dc. We'll get the core diameter. Okay, so once this core diameter is obtained, it is very easy to find the nominal diameter by using the relationship d is equal to dc divided by 0.8. So it is as simple as that. Okay, all you have to do is to remember these two equations. Now let us move on to the design of the cap thickness. So with the same figure, let us move on to the design of the cap thickness. Okay, the TC over here is the cap thickness. The same PI max pressure is acting over here. Okay, now to determine this one, let us assume this complete setup to be a simply supported beam which is supported using two bolt. Okay, and a peculiar shaped beam is there, and pi max load is acting at the center, and the distance between the two bolt centers, let it be L. Okay, so in that condition your moment acting on this one, or the maximum moment which is acting, can be obtained using the relationship mb is equal to pi max into L divided by 6, where pi max is the maximum inertial force acting at the center, which you can find it out. Okay, and L is actually the span or the length as shown in the figure. So to find this length, all you have to do is you have to sum this length with this extra length plus over here plus the half or the diameter of the bolt. Okay, so it is given here, that is L is equal to length of the crank pin, which is the length of the crank pin. This is the length of the crank pin, followed by 2 times thickness of the bush, 2 times thickness of the bush will be adding, and approximately it is 3 mm plus the nominal diameter of the bolt, that is half diameter is over here plus half diameter over here, which will give you the nominal diameter, and plus it is added with a clearance with a value of which is 3 mm. Okay, now once this is obtained, we can we can determine the thickness using the standard relationship for the permissible bending stress. Since it is a bending stress, we'll go with a very standard equation, that is bending stress is equal to mb divided by I into y, where mb is the maximum moment acting at in the beam, and I is the moment of inertia of the I section. Okay, the moment of inertia of the section, and for I is the moment of inertia of the section, which this section, okay, of this section, and y is the distance from the neutral axis from the section. Okay, so I is nothing but BC into TC cube by 12, where BC is a width which is not shown here, and TC is the thickness which is to be found out. Okay, and y is equal to TC by 2. Okay, so substitute all these values in the equation, and on equating both the equations, you will be getting the thickness. Basic design procedure is coming to an. So with this, the basic design procedure is coming to an end. Now let us find out how to find the whipping stress acting on a connecting rod. So what exactly is this whipping? Okay, so to understand this, let us see this the working of this connecting rod. See, one part of this is connected to a connecting rod, and the second part is connected to the crankshaft. So the motion of the connecting rod is something like this. The part which is connected to the piston will be executing a reciprocating motion, whereas the part which is connected to the crankshaft will be rotating a circular motion or a pure rotatory motion. And because of this, the parts intermediate to this connecting rod will be executing an elliptical path, and due to this difference in motion, it produces a lateral oscillation, and this oscillation induces an inertial force, and this causes bending of the connecting rod, and this is called, and this bending is actually called a whipping. Okay, and the stress associated with this whipping is called whipping stress. Okay, so to determine this whipping stress, see, since it is a bending stress, let us use the very basic or very fundamental equation, sigma b is equal to mb by I into y, right? Where your mb is the maximum bending moment acting on the connecting rod, and I is the moment of inertia of I section with respect to x-axis. Okay, so for this you can refer the PSG data book. The value is, you will get the value as for 419 by 12 into t raised to 4. Okay, it is actually the moment of inertia of the I section. Okay, since we are dealing with the shank portion, right? And y is the distance from the neutral axis, and this also you can get it from the data book, right? So this will be complete. The bending stress or the whipping stress can be found out only if we get the maximum bending moment. And to get the maximum bending moment, we have a standard equation which is given by m1 omega square r into L square by 9 root 3. This is a standard equation, and where m1 is the you have to by heart this equation, and m1 is the mass of the connecting rod per meter length, and can be obtained by multiplying area with the density. Okay, and area is 11 t square, and rho is the density, and it can be taken as 7800 kilogram per meter cube, since it can be taken as we are considering steel, right? And finally, the r is the radius of the crank, and L is the length of the connecting rod. So with this, and on substituting all these values, you will get the maximum bending moment, and on substituting all these values in the bending stress equation, you can get the whipping stress value. So with this, the complete connecting rod design is coming to an end. Okay, this is it. You have to do all these basic 4 steps plus whipping stress. Once you complete all these 5 steps only, the complete connecting rod procedure is over. It can be given even as a 20-mark question, right? Or each part can be given as a separate separate portion to solve. And this complete the complete procedure is taken from uh, machine design of machine element textbook by VB Bandari. Okay, there will be different procedures depending upon the data book, but most of the equations are not there in the data book, so better follow this procedure. And this is a very, very, very important portion as far as your module 6 is concerned. So thank you, thank you, thank you very much.